Hiding information in noise. Fundamental limits of covert wireless communication. Here are our references. We mainly focus on the first one, and there are other references which are listed as follows. Encryption-based security prevents unauthorized decoding, but does not ensure undetectability of communication, which is crucial in many cases. Various covert communication techniques have been developed to address these concerns, including steganography for finite alphabet noiseless applications and sprite spectrum systems for wireless communications. This article discusses new results on the fundamental limits of their capabilities and provides a vision for the future of such systems as well. Secure communication systems should also provide covert, stealth, or low probability of detection intercept communication. Such systems not only protect the information contained in the message from being decoded, but also prevent the adversary from detecting the transmission attempt in the first place and allow communication where it is prohibited. The overachieving goal of covert wireless communication research is the establishment of shadow networks, which is illustrated in the Figure 1. They are assembled from relays that generate, transmit, receive, and consume data, and jammers that generate artificial noise and impair the ability of wardens to detect the presence of communication.
In this diagram, Alice is transmitting signal to the intended recipient, Bob, while hiding it from the adversary, Willie. The practice of hiding sensitive messages in innocuous objects is known as steganography. In modern digital steganography, conceals messages in finite length in a finite alphabet cover text objects, such as images or software binary code. Embedding hidden message in cover text produces stegotext, which changes the properties of cover text. Stagger analysis, which is a countermeasure of steganography, look for these changes in the properties of cover text. Willie is assumed to have a complete statistical model of the cover text. The amount of information that can be embedded without being discovered depends on whether Alice also has access to this model. Assuming that Alice has access to this model, positive rate steganography is achieved given a bit O or N bit secret key that is shared with Bob prior to embedding. Bit O of N bits can be embedded in an M symbol cover text without being detected by Willie. Assuming that the complete statistical model of the cover text is unavailable to Alice, then Alice can safely embed BO of square root n log n bits by modifying BO square root n symbols out of n in the cover text, at the cost of pre-sharing BO of square root n log n secret bits with Bob. Note that this square root law of digital steganography yields zero rate steganography since it results to 0 bit per symbol. Next, we look at the problems of steganography. Steganography is inherently an application layer covert communication technique. As such, the result for it has limited use in the physical layer covert communication. First, analysis of steganographic system generally assumes that stenotext is not corrupted by a noisy channel. Second, the generalization of the result of steganographic systems is limited because of their finite alphabet discrete nature. Third, by embedding the hidden message, Alice replaces part of the cover text. While this effectively enables the recent positive rate steganography method, it cannot be done in standard communication system unless Alice controls Willie's noise source. Finally, the most serious drawback of using steganography for covert communication is the necessity of transmitting the stenotext to Alice to Bob, a potentially unrealizable requirement when all communication is prohibited. We thus consider physical layer covert communication that employs channel artifacts such as noise to hide the transmission. Next, we look at one technique of stenography. The spectrum approach involves transmitting signal that requires a bandwidth Wn on a much wider bandwidth compared to Ws, thereby suppressing the power spectrum density of the transmission below the noise floor. Spectrum system provides both covert communication capability as well as resistance to jamming, fading, and other forms of interference. Topical spectrum techniques include direct sequence spectrum and frequency hopping spectrum and their combination. In direct sequence spectrum, the signal waveform is multiplied by the spreading sequence. The spreading sequence is randomly generated binary waveform with a substantially higher bandwidth than the original signal. The resulting waveform is thus spread over a wider bandwidth. This reduces the power spectral density of the transmitted signal, as you can see in the figure. Bob uses the same spreading sequence to despread the received waveform to obtain the original signal. The spreading sequence is exchanged by Alice and Bob prior to transmission and is kept secret from Willie. In FHSS, the carrier frequency is retained for each transmitted symbol. The frequency hopping pattern is also randomly generated and secretly shared between her and Bob prior to transmission. FHSS can be combined with orthogonal frequency division multiplexing, enabling the use of multiple carrier frequency. To further reduce the average transmitted symbol power, FHSS can be used with time hopping techniques that randomly vary the duty cycle. The time hopping pattern is also secretly pre-shared between Alice and Bob prior to transmission. The operation of FHSS with OFDM and time hopping is illustrated in the figure. In square root law for covert communication over additive white Gaussian noise channels, we determine just how small the power has to be for the communication to be fundamentally undetectable, and how much covert information can be transmitted reliably. In standard model for free space RF channel, suppose that the channel from Alice to Bob and to Willie are subjected to AWGN with respective variance B greater than 0 and W greater than 0. Let N be the total number of channel use available to Alice and Bob. Assuming Willie observed these N channel users, when Alice is not transmitting, Willie observed AWGN with total power variance N over N channel observations on average. By standard statistical argument with high probability observations of the total power lie within plus minus C variance W square root of N of this average, where C is a constant. Since Willie observed Alice's signal power when she transmits, in addition to noise power, to prevent Willie from getting suspicious, the total power that Alice can emit over N channel use is limited to big O variance W square root of N. Otherwise, her transmission will be detected. This allows her to reliably transmit big O variance W square root of N over variance B, covert bits to Bob in N channel use.
Digital covert communication. The DMC model assumes discrete input and output. The memoryless nature of the DMC means that its output is statically independent from any symbol other than the input at that time. Here is an illustration of DMC model. Binary symmetric channel restricts the DMC to binary input and output alphabet of 0 and 1. It has been shown that while no more than O square root n covert bits can be reliably transmitted in NBSC uses, if PW is larger than PB, the pre-shared secret is unnecessary. The reason why this can be achieved is that a more intricate analysis of random binary codes is carried out, This involves a novel and intricate analysis of concentration inequalities. Here is a comparison of related works. For DMC channel in Hall and Kramer's work, the precise secret is not necessary. For BSC channel in Chi's work, the precise secret is also unnecessary. Channel resolvability can be employed to generalize the square root law to DMCs. Channel resolvability is a minimum input entropy needed to generate a channel output distribution that is close to the channel output distribution for a given input. Resolvability has been used to obtain new, stronger results for the information theoretic secrecy capacity. Here is an illustration of channel resolvability. The key S is used to select one of the key codebooks containing M code words for encoding message W. The underlying idea is then to guarantee that each codebook is sufficiently small to ensure reliability over the main channel while ensuring that there are sufficiently many distinct codewords overall to keep the warden confused. If the channels from Alice to both Willie and Bob are DMCs, and Willie's channel is worse than Bob's, techniques in 2 and 4 can be used to demonstrate the square root law without a precise secret. Furthermore, as long as Alice to Willie's channel is known to Alice, all square root n precise secret bits are sufficient for covert communication when Willie's channel capacity is greater than or equal to Bob's. The results in 5 apply to AWGN channels as well. Willie's ignorance of Alice's transmission time allows her to transmit additional information to Bob. Surprisingly, under some mild conditions on the relationship between the total available transmission time and the transmission duration, Alice and Bob do not even have to prearrange the communication time. Positive rate covert communication. This occurs when Willie either allows Alice to transmit messages containing information or is ignorant of the probabilistic structure of the noise on his channel. Incompleteness of Willie's noise model can also allow positive rate covert communication. Some of the results for point-to-point covert communication in the presence of a single warden can easily be extended to scenarios with multiple independently controlled receivers. Our ultimate objective is to enable a wireless shadow network composed of transmitters, receivers, and friendly jammers that generate artificial noise, impairing wardens' ability to detect transmissions. Completing the characterization of the point-to-point covert link in a multi-warden, multi-jammer environment is an important step toward understanding the behavior of shadow networks and their eventual implementation.